So just a reminder, you're gonna have exam on Monday, right? This Monday?
No. What?
No.
The day after this, after this weekend.
Oh.
Yeah.
Oh, but
So, the 11th?
I was about to
No,
be like,
following Monday.
oh, November 11th, y'all.
Yes, so
Like, I can't turn around that quickly.
November 11th gonna be the exam. So I'm gonna post the questions on Blackboard by tonight, probably in the afternoon sometime. Okay? So you're gonna have 2 whole weekends to review it. And then, what do you prefer? Review in 1 class or 2 classes? 2 classes?
Yes.
Alright, so I need to speed up a little bit for the lecture if you wanna do that. Because after 11th, you're gonna have about 2 weeks for the next exam, right? So next gonna be December 4th, something like that. So, yeah, you're gonna have 2 classes, I can do that. That's fine. Yep.
Can we still do part of 11 though?
Part of-
For this exam? Can we do part of chapter 11?
Probably the first part of that. So I'm gonna write that in the announcement. So what to cover, okay? We're gonna see on Monday how we're gonna cover it, and then we're gonna decide based on that. Okay? All right? Okay, so now I'm gonna explain in a little bit detail for this reaction. So this concept applies to all other reactions for one, right? So whenever you say the reaction of alkene with different reagents like HBr, Br2, water, boration, oxymercuration, so all those reactions you have for alkene, same applies for alkyne. Okay? So sometimes you're gonna have one step further than that. So that's what I'm gonna stress a little bit more. But for the other, the same thing. So probably I need to spend more time on that, right? So, okay. Let's say this one. So you're gonna add the hydrogen on triple bond, okay? If I write one reaction for alkene, say I'm gonna take the same, actually it is over here, this is alkene, right? So this is alkene, you have, when you add the hydrogen in presence of catalyst, what's gonna be the product? So you're gonna add hydrogen on the double bonded carbons. So you're gonna have 2 more hydrogen than alkene, right? So that's gonna give alkane. So that's the product. Right, so this is standard. So that's the one we learned in alkene. Okay? So here what we are doing is we are adding 1 more steps on that. Right? You are not starting with alkene. You are starting with the triple bond, not the double bond. Okay? So I'm gonna write the same. So for example, this, and then I'm gonna have the triple bond over here, and then I'm gonna write this. Right? So if you compare the first written molecule, which is alkyne over here, right? So this is alkene, the second one, and then the third is alkane, right? So now, if I do the H2 addition on that, say palladium catalyst like before, okay? So what are you gonna do for that? You're gonna add 2 hydrogens because you have 2 hydrogens in 1 molecule, right? So you're gonna add that to the triple bond. So 1 bond gonna take 2 hydrogen atoms. Okay? So if I write with the different color, so I'm gonna write these 2 hydrogens or H and H. I'm gonna add those in these carbons over here. So that's what it is. 2 hydrogens over here, right? So now, do we see any difference if we compare to the alkene? No, right? So in the previous chapter, that's the one we covered. So this is previous chapter, right? So this is previous chapter. Now, whenever you say the triple bond, you're going to add this to that. You're going to add that. And then you have the same reaction after that. Right? So now, in the exam, it is a little bit tricky. Okay? Be very careful how many molecules you have. So in the chemical term, you're going to say the how many equivalent. So that's the name we're going to call that. So if you have alkane like over here, let me write the 2 questions based on that. So this one I'm going to have the H2 and then palladium. Other, the same starting material you have. So I have 2 H2 and then palladium. So you're going to have the different product. Okay? So this is called the equivalent. So whenever you see the coefficient over here, so this is equivalent. LENT, right? So like something like this. Okay? So that means you have the 2 molecules of hydrogen for 1 molecule of alkyne. So if you have that, you're going to go all the way to alkane. That's going to be the part. Because you have 1 molecule over here plus another over here. You have 2 total. Okay? So add 4 total hydrogen atoms on that. And then you're going to go all the way to the alkane. That's going to be the final product. Okay? But if you don't have 2, you have only 1 hydrogen molecule. So by the time you go to alkane, the middle atom, middle molecule over there, 1 molecule is done, right? You don't have any more to go to the 3rd one. So your product is going to be alkene, right? So this is going to be the double bond like that. So 2 hydrogens over here, right? And then the 3rd one is going to be alkane. So don't be confused with that. So you have 2 hydrogens over here, 2 hydrogen. So now you see the product difference, right? So this is going to be sometimes tricky. So be very careful how many reagents are there. Okay? Whether you're going to stop in alkene or you're going to go all the way to alkane, depends how many equivalent you have there. Okay? So, now, once you know that, then other going to be similar to that, right? Okay, one more thing. Okay. So here, when you go from alkyne to alkene, if you pay attention to this structure over here, like this, is it cis or trans? Cis, right? So why you always gonna have cis, not the trans over there? Because the double bonded carbon need to be adsorbed on the catalyst surface. Okay? If you have the trans, the carbon cannot reach there. The other bonds gonna seal the contact between the surface and the double bonded carbon. That's the reason why if you have the solid catalyst, okay? If you have the solid metal, so the molecule is gonna be absorbed on the metal surface, always gonna be cis. There is no trans product at all. Right? That's the reason why if you see the molecule over here, This is the orientation. Okay, so actually if you draw in 3D, you're gonna put the bronze in one side of the double bond, and then the hydrogen gonna be in the other side, right? So that's gonna be the case. So you're gonna have the same product if you use the other reagent, like this one. Sometimes you're gonna call the Lindlar catalyst, that's the name for that. So sometimes the question can only give the name without those molecular formula of the reagent. Right? So make sure you memorize that. So this is the name for that. So here, instead of writing all those, just it can be like this, Lindlar catalyst. Okay? If you have that, you're gonna have the same product. Why? You have this solid metal over here, you're gonna have the same mechanism like before. Okay, so you have the solid metal, so the molecule is gonna be absorbed on the surface, so it's gonna be cis like before, right? So the same cis alkene is gonna be formed. But if it is not solid, if it is the dissolved metal, like say sodium chloride for example, you can have the table salt solution. So sodium metal gonna be in the ion form, Na plus. This is the dissolved metal. Okay? If you have that, then the story is different. So for that, for the dissolved metal case, you're gonna have the trans, because the molecule doesn't need to be absorbed on the surface in a plane, right? So metal is everywhere in the solution. So it's gonna give the trans. It's still gonna be alkene. The nature of product is not different, but the orientation is gonna be different. Cis versus trans. Okay? So that's the one you're gonna keep in mind. Now for the summary of the other reagents, like alkene, so you're gonna have a very similar reaction like this. Right? So if you recall, you have the HX or HBr, HCl addition on that, right? Or you could have the hydration, water, in presence of acid. You could have the BS3, you can have the Br2 or X2 halogen molecule, right? Halogen addition. So those are the reactions we covered in alkene. Now we're gonna have the similar thing over here. We're gonna have the similar part. Remember the easy example before, the hydrogen addition. Equivalent. Okay? So alright, so let's quickly, I'm gonna go pretty quickly unless there is some extra step other than the alkene. Okay? If you have any extra, I'm gonna stress on that. So now the first is HX addition, so HBr, HCl. Right? If it is alkene, what do you do? So let me write the same molecule in the alkene form. So you're gonna have this, and then you're gonna have the double bond. So you're gonna have the hydrogen there, right? So you're gonna have two hydrogen. Oops. So two hydrogen there, and then you're gonna have one hydrogen over here, right? So this is alkene. So if you do HBr for that, so what is gonna be the product? That's from the alkene chapter, last chapter, right? So remember the double bond gonna act as nucleophile. So you can think that way. So bromine is more electronegative. So they're gonna make a bond of that. It's gonna retain in bromine. You have the bromide nucleophile after that. You're gonna have the carbocation, and you're gonna make the bond. Right? That's all the detail of that. But shortcut, hydrogen gonna go to one double bonded carbon. Bromine is gonna go to the other double bonded carbon. That's the product. Okay? So now the question is which carbon? So bromine gonna go to which carbon? 1 degree or 2 degree?
2 degree.
2 degrees. So you're gonna put bromine over here in the middle, and then the hydrogen is gonna go to the end carbon. Okay? So you're gonna do the same exact thing over here. Right? So you have the triple bond, you're gonna do the H and Br addition. So where the bromine is gonna go? 2 degree carbon like before. So that's why you're gonna add bromine over here. Exactly like alkene, right? And then now the question is always equivalent. How many HB are there? If you have only one HBr, the reaction is going to stop over here. You don't have any more HBr to react, right? So for 1 mole, if you have 1 mole HBr, product going to be the alkene derivative. Okay? If you have 2 equivalent, then you're going to go further from there, and then you're going to have another Br added to the 2 degree carbon. Okay? So dibromide alkane, alkyl dibromide, going to be the common name. Okay? That's going to be the product. So dihaloalkane or dibromoalkane or dibromide. So that's going to be the product, right? So remember here, equivalent. 1 equivalent or 2 equivalent. So whenever you have the arrow, so be very careful over here in the arrow there. So how many? If you say just 1 HBr, you're going to stop over here. If you have 2 HBr, you're going to go further. Okay? So that's the thing. So now, the one difference compared to alkene is you can have different types of alkyne. Remember, you have the terminal, you have the symmetric or the unsymmetric, you have different types, right? Based on that, you're gonna have the slightly different proportion of the substituent, right? So what I am focusing on that is, if you have the terminal, this is the one, because this is terminal, right? You have the triple bond at the end, so this is terminal alkyne, so that's going to be like alkene. But if it is not terminal, then you're going to have slightly different than the other one, like this, right? So symmetric, you're going to have 2 degree on both sides, doesn't matter, okay? So if you have the one symmetric, so what you're going to have is, you're going to have this carbon and this carbon. So what degree is that? 2 degree. This one, 2 degree. Right? So then, which carbon you're going to add the hydrogen? Which one you're going to add the bromine? You have the 50-50, you have the same 2 degree carbon atoms, right? So this is by chance probability. You're gonna have either you're gonna have the hydrogen over here, or you're gonna have the hydrogen to the other side over here. So this is to the right, and then this is to the left side of the double bond. You have the equal possibilities to add that. So you're gonna have the mixture of the product. Okay? So you're gonna have the 50-50 mixture when you have that type of scenario. If you have the symmetric, you're going to have the same product, doesn't matter, it is not different. Whether you are to the right or left, you're going to have the same product. But if you have the unsymmetrical, then you're going to have the 50-50 mixture. Right? You don't have any preference for the hydrogen or bromine, where to go. That's the difference. Then alkene. Okay? Okay, one thing. So geminal. So this is the chemical name to indicate the carbon. So if you have any substitution in the carbon, so here it is for bromine, but you're going to apply for any substituent you have. Okay? if you have the substitution on the same carbon, I mean more than one substitution, it is called the geminol. Right? That means you have the carbon on this bromine on the same carbon like this. So this carbon, you have two bromine over here, right? So this is geminal carbon. Okay? So that is called the geminal. So it is not saying for this, actually it is saying for the symmetrical or the terminal, for both. Because you're going to have both on the same carbon. Okay? Alright, so then we complete that. Alright, this is another difference. Then alkene. So before we go to the reaction, so let me define one term, so it's going to be easier to go in the reaction. So ketoenol. So this is called the tautomerization. So it is like autoionization of water. So equilibrium. So you're going to have the one or other form, just keep interchanging one to another, right? So ketone, whenever you have the double bonded oxygen to the carbon, so this is keto group. So this refers to that, the carbon oxygen double bond. Okay, this is keto group. And then enol, you're going to have the carbon-carbon double bond, and then you have the alcohol group on the carbon that has the double bond in it. So this is enol. So that is alkene and alcohol together, right? So alkene and alcohol. So this OL for alcohol, and then EN for alkene. So this, so enol. That's how it is named over here. Both. You have the alkene and alcohol, but remember, you cannot have alcohol in one part of the molecule and then the double bond to the other carbon. No. So whatever carbon you have the double bond, alcohol have to be on the same carbon. Alcohol on the double bonded carbon. If you have that, that's the enol. Okay? Now, when you have molecule of this type, you're going to have the resonance. Okay? Let's say this one. So this is enol, right? So why this is enol? You have the carbon-carbon double bond on the same carbon. You have the OH group there. That's enol. Okay? When you have that, then you're going to have the rearrangement, so that the double bond going to go to the carbon, and then the hydrogen going to move to the next carbon, right? So this hydrogen going to move over here, carbon number 1, for example, label, and then double bond going to go to the carbon oxygen, right? So what is that? That's ketone, right? So you have the ketone and enol, you're going to have the equilibrium. This is because of the resonance of the double bond you have between carbon-carbon and carbon-oxygen. Okay? This is called the keto-enol tautomerization. So you're going to have the one favored by the other depending on the condition you have in the solution there. But it's going to go in both sides. You're going to have the mixture of both. If you take this sample, you're going to have the ketone form, you're going to have the enol form, you're going to have the mixed of that. Okay? So now, whenever you have the alkyne, then you're going to add the OH on that, you're going to see this for all reactions. Right? What I'm referring to is, suppose you have triple bonded carbon over here. That's the focus. Okay? So now I'm going to add OH there, So let's say H2O there, and then you have the catalyst. So just I'm gonna write catalyst. You can have one more catalyst than alkene, like phosphoric acid or the mercury acid, mercury sulfate. So now this one gonna give the OH, right? OH and H. So you're gonna have that to the one carbon and then H plus to the other carbon, like before, like alkene, right? Then what gonna be the product? So I'm gonna write the different color. So gonna be less confusing. So this one and then this one. So now I'm gonna add OH over here, and then I'm gonna add the hydrogen to the other side. So what gonna be the product then? So you're gonna have double bond, and then you're gonna have substituent over here. So the same molecule, right? And you have the hydrogen, right? So the hydrogen is gonna be over here, right? That's the product, like alkene. So if you have alkene and you have the water, hydration, what do? You're gonna add the hydrogen to one double bonded carbon and then the OH to the other double bonded carbon, right? You are doing exactly same thing over here. You have the pi bond, so add one hydrogen to one carbon, OH to another, right? So OH to which carbon? More degree carbon. So you're gonna add 2 degree carbon OH there, hydrogen to 1 degree carbon, right? So this is same as HBr, HCl, hydration, the same mechanism. Yep.
If there were 3 degree carbon, would this, is there a possibility of a hydride shift or no?
For the alkyne, no. Still you have the double bond over there. If you don't have any double bond and then all carbon and equivalent, yes, you can have the rearrangement, either hydrogen or methyl shift from there. But for the alkyne, until other pi bond is taken care of, you don't have that. Okay? So now, here, those keto-enol thingy, now I'm gonna apply over here. Right? So now you're gonna make the product based on that. So that's why we need to know the keto-enol, ketone and enol, right? So it's gonna make the ketone product. So now let's see the reaction once you know that. So now you're gonna have, so this one additional catalyst. So this is the new on that. So this is catalyst. So before, for the alkene, remember this is alkene. So this is for alkene. So this is not this chapter, just to compare it. So this is previous chapter, right? So acid was catalyst. You have the water there. So you're gonna add OH and H. So hydrogen to the one carbon, and then the OH to the other carbon. So you added that, right? So now you're going to do the same thing, but you're going to have one more catalyst because reaction is going to be very fast, very slow because triple bond is stronger than the double bond. So you need to have the catalyst. So now you're going to have the similar reaction. So I'm going to draw that. So I'm going to have, let me draw the different color. So I'm going to draw in the same way like it is written over here. So you're going to have that, and then you're going to have the carbon-carbon double bond, and then you're going to have the hydrogen there. So what you're going to do is you're going to add, like alkene, you're going to do the same thing, carbon 1 and carbon 2. So 1 and 2, you're going to add the hydrogen to 1. So I'm going to add that hydrogen, and then OH to the other one, right? So this is going to be exact like alkene. Okay, so now since you have the keto-enol tautomerization, what's gonna happen is this hydrogen gonna go to the other carbon, and then the double bond gonna go over there. So you have the ketone product. This is one extra step than alkene, right? So when you see the product, don't think it is different, like an entirely different reaction. The same as alkene. You have the one extra step on that. You're going to do the same as alkene, plus you're going to move the hydrogen of the alcohol to the other carbon, and then the double bond to the carbon oxygen, so it is ketone, right? One extra step, right? So what's going to be the product? If you have alkene, you're going to have the alcohol. If you have the alkyne, first you're going to have the alcohol like alkene, then it's going to change to ketone after that. Right? Alright. So this is hydration. So this is the mechanism for the oxymercuration, right? So where do I say that? So if you have the oxymercuration, what are you going to have? Alcohol, right? So here you're going to have the alcohol like before, plus one extra step, ketone, right? Same as the previous one. So the final is going to be the ketone, right? So until the alcohol, so this is same as alkene up to here. So same as alkene up to over here. So this is extra step. Ketone is extra. So up to enol, you're going to follow the exact same as alkene. There's no difference at all. Good? Alright, so now hydroboration. So here also you're going to have slightly one step different. So let me review alkene first, right? So suppose you have that alkene, and then you're going to have the BH3. What do you do? First, you're going to have the alkyl group attached to the boron. So boron is going to have the empty orbital. So you're going to bond that to the double bonded or triple bonded carbon, right? So whatever group you have, so this carbon over here, so this I'm talking about the alkene, right? So let me remember one. Just I'm writing the alkene double bond. So for that, so now what's going to be the product? So take this carbon number 1, right? You're going to add this carbon to boron, right? And then the hydrogen to carbon number 2. That's what you're going to do, right? So you're going to have the hydrogen over here, and then you're going to have the boron, and then you have 2 more hydrogen with boron as is. So you have that. That's what you did in alkene, right? So now, since you have 2 more hydrogens, there is no other double bond in the carbon, you're going to do the same thing for this hydrogen to replace this hydrogen. So you have the trialkyl borane. They are going to be the product, right? So you're going to replace that with the same alkyl group, that with the same alkyl group, and then finally you're going to have the alcohol, right? So here, the first step is same as that, like before. So you can have the slight difference after that. So now let's see triple bond. So BH3, what are you going to do? You're going to do the exact same as alkene. So carbon number 1, carbon number 2, So you take the boron, you're gonna connect that to carbon number 1, right? Carbon 1, carbon 2, and then the hydrogen of boron goes over here, carbon number 2, that's the hydrogen from boron, and you have BH2. So up to this, same as the previous chapter, no difference at all. Right? So now, here, what's going to happen is adding another alkyl to the boron or another BH3 molecule. So you're going to have the competition of that. So you're going to have this, because of the double bond you have, another BH3 going to be added over here. So you're going to have the 2 BH3, right? So for BH3, you're going to have the BH2 and you have H, you can write that way. So same as before, the hydrogen is going to go to the carbon 2 and then BH2 is going to go to the carbon 1. So that's what you take. Carbon 1, carbon 2. Okay? So since you have 2 double bond, you're going to have the duplication of the previous chapter until you have the single bond. Okay? So now, this is possible, but you're going to have complicated because you have 2 boron group over there. So that's going to make the reaction with a different byproducts. You have the 2 bromine centers over there, right? So you're going to have like a mixture of the products. So to simplify that, sometimes we're going to use the different reagent. So we're going to seal the bromine from 2 bulky group and then we're going to react with only 1 boron. So it's going to prevent the further addition of boron there because of the bulky group. Okay, so this is the strategy we use to do the advanced synthetic technique, something like that. But here you don't have to worry about it. So just remember that this gonna give the mixture of products. Okay? So that's the extra. So now after that you're gonna have the OH formation, same as before. So you have H2, you have OH to the double bonded carbon, right? So it is anti-Marconi curves, you only know that because OH is on the 1 degree carbon rather than 2 degree. Okay? Alright, so the next gonna be bromination and chlorination. So again, this one also, you're gonna have the same step like before. We can think this like S2 addition. So do you remember what is going to be the product? If you have, say, double bond like this, and then you're going to have the, let me write this way, Br2. So this is alkene, you have Br2, what is going to be the product? You're going to add bromine to the carbon, right? So, dibromide, right? Like this, you have the 2 bromine in the carbon, right? So if you have the triple bond, what are you going to have? You're going to have the 1, 2, 3, 4. Maximum you can add 4 bromine atoms over there. So you have 1, 2, 3, 4. So you're going to have the tetrabromoalkane. When you have the alkene, you have the dibromoalkane. Now you have the tetrabromoalkane, right? Again, so when you see the question, be very careful. So if you given like a Br2, so what is over there? If you have the 1 equivalent, you're going to have the dibromoalkene. If you have the two equivalent, then you're gonna have the tetrabromoalkane. Okay? So this is dibromoalkene, right? So this is gonna be the product when you have the one equivalent. Only one molecule. Okay? So if you have the tetrabromoalkane product, then you're gonna have the two equivalent. That's the difference. Yeah.
Like on the example, you see the arrow with the 2BR2?
Yeah. So for example here, so let me write this way. Like this. And then if you have the 2BR2, then your product gonna be this one. You have the two equivalent over there, so you're gonna be tetrabromoalkane, gonna be the product. Right? This is same as hydrogenation. So if you have the one equivalent, you're gonna have the alkene. So you have the alkene, bromine substituted, right? If you have the two equivalent hydrogen, you're gonna have alkane. So you have the alkane with the 4 bromine in it. So for hydrogenation, you have 4 hydrogen. So bromination, you have 4 bromine. That's it. Right? All right. So now, synthesis. So now, we learn some alkane reactions, right? And then alkyne reactions. So now we have different types of reactions, right? So now if you want to convert one reactant or one compound to the other compound, so you have different possibilities. Okay? So sometimes to make the one compound, there is no one unique way. You can have a lot of possibilities to make that, right? The question is whether it is efficient, whether you can have the mixture of product or the unique major product you have, or type of the catalyst you're going to use. So what is the economical aspect on that? You're going to consider all those things, and then you're going to choose the best one, right? So this is called the synthesis approach. So when we do that, sometimes if you want to make something, so the final product, we're going to start from there and then we're going to go all the way to the back and figure out where to start, right? So this is called the retrosynthesis in the chemical name. This is going to be something like this one, right? So for example, you want to make this as an example. So how are you going to make it? So you can make from this one, right? You can make from this one. You can make from this. You can make from this. So where do you start? So many different possibilities, right? So this reaction is going to be kind of alkene summary. You have summary of all the alkene reactions with the different reagents. The other going to be the alkyne reactions, right? So you have different products. So you can have the conversion from one to another. Okay, so that's how we see if we want to prepare the new compound, right? So now let's see one thing as an example. So let's say we're going to prepare this, and then we're going to prepare from the alkane. Let's choose this route over here. So we're going to go from here. So let's choose the alcohol. So from here, we're going to make the alcohol, not from alkene, directly from not from alkyne, directly from alkene. Okay? We are not making from this, let's make from this one. Okay? So now when you see this, you have alcohol over here, right? So you have the different options. You have alcohol from here. So you can make varieties of different ways. Right? So what you can do? You can write different things over here. So this is alcohol. So you're going to do the hydration in presence of acid catalyst. Okay? And then you can do the hydroboration. So you're going to have that reaction. It has alcohol there. And then you're going to have the oxymercuration. So this is the product you have. Right? So now, which one you're going to choose? It depends whether you're going to have the mixture of different types of alcohols or whether you're going to prefer one particular degree of alcohol, 1 degree versus 2 degrees, something like that, right? In this question, it is 2 degree alcohol, right? So you're going to make 2 degree. So we're going to make the alcohol on the second carbon from the end. So you're going to put over here, right? So then, at all other possibilities, you're going to discard that because you don't want to make 1 degree alcohol, you're going to make 2 degree alcohol. Okay? So because this is going to give the anti-Markovnikov's product. Right? So this is anti. That's why you're going to have the OH to the 1 degree carbon. Right? And then other 2 possibilities, you can do either one. Both going to give the same product. But you're going to have the some mixed with the product, the mixture of product is still major and minor, but not 100%. Right? So based on that, you're going to choose which one you're going to use. So for the first one, you're going to have the maybe 1%, 99% mixture, something like that. Right? So both carbons are free. 2 degree carbocation is going to be stable. But depending on the average kinetic energy of the system, still you're going to have few product with the 1 degree alcohol, right? So the measure is this 2 degree. If you don't have that, so a little bit of 1 degree is not a problem. You can do that. But if you have the strict 100% 2 degree alcohol, then you're going to use this one, right? Because remember oxymercuration, you're going to have the mercury bonded with the 2 carbon over there. There is no carbocation formation, nothing. So you're going to have the alcohol in one particular carbon. This is 100% alcohol. You don't have any mixture of other alcohol there, right? Something like that, right? So even if we can make the compound in different approach, we're going to choose the right one based on what you are looking for. So this is called the synthesis. So you know that because you did aspirin synthesis, right? So this is simple, but you're going to have the many steps synthesis. As we go through different chapters, we're going to cover the different functional groups in it, and you're going to have more and more conversions after that, right? All right. With that, this chapter is done.